Hi. Yeah, this is kind of a follow-on to Brian's talk, and I am going to need you to display my slides locally in the room there.
Okay, Carol, stand by. You're all set?
Okay, so there are two missions coming up on the moon in the next year that use the Trident drill. So what I'm going to talk about is lessons that we've learned for those missions from recent field and lab tests using the Trident drill. So next slide. So the field work I'm going to talk about was actually part of the AREDS P-STAR. Brian Glass was the PI of this mission, or this activity, and it went on for 4 years in the Atacama Desert of Chile. In the fourth year of the P-STAR, kind of as our final performance, we did a mission simulation where we had a science team located in California that picked out a site based on Google Earth imaging, and then that site was sent, field team was sent to that site, and they they set up near it. And basically the site was a playa basin that was flooded at some time in the past. It was surrounded by a desert pavement. When the field team got there, and the playa basin is the light colored stuff, and the desert pavement is the dark colored stuff. When the field team got there, they flew a drone flight over the site and actually got topography. So based on that, the science team picked out 3 locations for drilling, and 2 of them were in this basin location, and the third one was on the desert floor. So go to the next slide. This is the equipment that we used for the field test. We had the Trident drill mounted on the K-Rex rover. It also had a robotic arm with a scoop and a science payload that was actually life detection instruments that are located in the instrument bay. So the way the Trident drill works is it actually goes through a tube. The augers of the drill and the bit goes down through a tube, a hollow tube, through a foot that is actually sitting on the ground, and that helps stabilize it to get the hole started. As the drill rotates, it cuts the material, and then the auger flights push the cut material up through that tube, where it is scraped off by a cogwheel. And from the scraping off, you could put a robotic arm underneath it, a scoop underneath it, and capture the cuttings, and then deliver those to the instruments. Next slide. So this was a 6-day mission simulation. Again, we had the science team in California. In those 3 sites, we drilled to 80 centimeters, actually multiple holes, shallower depths, for different holes. But the way this was operated is that we had commands that were sent from California to this engineering team that was located in the field. And then the field team actually teleoperated the drilling system according to those commands. So it was kind of a hybrid between an actual Mars kind of simulation and a lunar kind of simulation. The operation strategy was adapted from the Mars 2020 Perseverance Ops Plan, which at the time that we did this, Perseverance had not flown yet. Next slide. So we did kept detailed track of everything that happened. Time and event logs were collected for all the holes. And so this plot here on the bottom is kind of like an event log for all the different things that were going on. Right in the middle, between 2 and 2, this is hours on the timeline, between 2 hours and 2 hours and 40 minutes, the drill was actually jammed. Next time step, we'll bring up a couple of other points. So in this particular case, everything took longer because we got the drill jammed. But the typical timeline to drill to 80 centimeters, including collecting samples and delivering to the instruments, was 55 command cycles. So teleoperation cycles is what you have to think about. The elapsed time, however, for doing this, even with the stuck drill, was less than 3.5 hours. So these kind of give you an idea of what the timeline of these upcoming missions is going to look like. Next slide. So Brian already showed this, but basically formation properties were inferred from the drill performance data. And the way this was done is actually just plotting the drill performance data. And this is weight on bit, rate of penetration, and auger torque. And then from experience, knowing that when it looks like this, it's in this kind of material. And that's from all the experience of all the different times this drill was used. And it had been used when we did this test for 3 previous years in the Atacama, drilling into all kinds of different materials. So this is kind of like a machine learning, only it's a human learning. It's done by the human recognition, but it is actually a candidate to apply machine learning to. And the next slide, so this is the last of the field data. So back in last year, we started doing drill tests in lunar simulants to actually get a better quantitative understanding of how to use this drill data for a probe of the material properties that you are encountering subsurface. And so we built a set of lunar simulants cemented with Portland cement, and another set of simulants, the white buckets in the back, in the picture on the right, that are very low porosity. They're a material called cellcrete. So it's like a very low porosity cement. And then in addition to that, we drilled some volcanic rocks. So the next slide shows data plotted from those simulants. So the points with the error bars are the simulant data. Down in the very low compressive strength, up lower left were the cellcrete simulants, and then the points with the red circles around them are the rocks. So basically using the things for which we had measured compressive strengths. So the simulants we all sent to a laboratory and got unconfined compressive strength measurements done on them. So following a procedure that was in a paper published by Peters et al. In 2018, where they applied a method like this to the Mars Curiosity rover, we basically fit a curve to the data, where the data is the specific percussive energy, which is derived from the drill measurements, against the unconfined compressive strength, and then fit a curve to those plots. And what you get is a nice, pretty simple logarithmic curve. And so with that, you can make an estimate of unknown materials by just knowing what their specific percussive energy of drilling those were. And that's what is in the red circles. So to go to the next slide, one of the things we discovered when we were drilling these simulants is that the drill jammed whenever we drilled into the lunar simulant, cemented lunar simulants, and it jammed at the same depth, 14 to 15 centimeters, regardless of what the compressive strength of those materials was. And when it jammed, before it jammed or as it was jamming, you heard a very loud squeaking sound, and the auger torque essentially went exponential. And that's the green line here, is the auger torque. And the dotted line shows this is where the squeaking occurred. So finally, I'm going to go to my last slide, which is conclusions from this activity. So we are learning that the formation unconfined compressive strength can be deduced from the drill data using a simple curve fit to the analog data. It could be more complicated, but this is the simplest way I could see to do it. However, this jam drill from the field experiment should be a chastening lesson for these missions. The jam drill happens very fast in the field. It took 67 operator commands with on-site feedback to free that drill once it got stuck. Maybe you can get a drill unstuck on the moon if you get it stuck, but maybe you can't. In the lab tests, the drill jammed 15 centimeters, and this was using the same bite sampling approach that is used for the Trident drill and that Honeybee plans to use for it on the moon. What we found is we had to take even smaller bites. Honeybee plans to take 10 centimeter bites. We took 8 centimeter bites, and on the second bite, we got stuck. We think it was actually the cuttings getting overfilling that tube that the drill goes through at the drill fit and getting stuck there. So they need to be cleaned more frequently. So what happens when you get stuck is you get a sudden increase in auger torque and loud squeaking. The drill should automatically stop and retract if this condition occurs, and that has to be automated. That's the end of my story.